Hello, everyone. So it gives me great pleasure to welcome Pierre-Henri Maire, who is actually an old guy from the lab because he did his PhD with Michel Dudek, for those of you who remember him, and also Rémi Santis. Rémi, Raphael, Romain Santis. Rémi Santis from CEA. From the lab of Limay, for those who know it, and now he is still at CEA and in Bordeaux, however, and he's a great expert of things that interest us as well: hyperbolic equations, interface tracking methods, etc. So it's with great pleasure that I give you the floor.
Thank you, Stéphane. I will take. First, I want to thank Stéphane for this kind invitation. I'm very pleased to be here because almost 30 years ago I have defended my PhD precisely in this laboratory. So it's come back to the beginning, not the end, I hope. Yes. And so I will try to convince you to dive into the marvelous world of hypersonic flows and the numerical simulation tools devoted to cope with these quite challenging flows. So the title is a little bit long, a Subface-Based self-centered finite volume scheme for solving the 3D compressible Navier-Stokes equation on unstructured grids using multi-point flux approximation. So I imagine that most of you know the finite volume word, okay? Here we will do something with finite volume discretization, which is a little bit unusual. And we will try to formulate another kind of finite volume discretization. This is the main topic of my talk, and I will show you the interest of doing this by evaluating and assessing the robustness of this method against various representative test case of hypersonic flows. Okay. So this is a joint work with Vincent Delmas. Vincent Delmas is our PhD student with Raphaël Loubert. And we are all living and working in Bordeaux, and this is a collaborative work between the Military Division Application of CEA and the Mathematics Institute of Bordeaux. So I will spend some time to introduce the subject, then I will recall you the compressible Euler equation, the notion of approximate Riemann solver, and then I will introduce what I call a non-conventional self-centered finite volume discretization. I will recall also some classical finite volume scheme, and then I will go to multidimensional numerical results, and I will try to accelerate for some parts in order to show the global panorama of this work. Okay. So let's start with the physical context. We are interested in the numerical simulation of hypersonic flows. There is a wonderful book by Anderson, okay, which explains all the features of hypersonic flows. Usually we are interested in blunt body configuration like this. So the structure of the flow is the following. You have a very strong curved bow shock in front of the nose of the body. You have a shock layer, okay, and a boundary layer. The specificity of this type of flow is that we have a very, very strong Mach number here. Usually when you are interested in re-entry flows for a shuttle, for a spatial shuttle, for instance, the Mach number is around 20 at the beginning of the trajectory. So with a Mach number of 20, you have shock waves which are almost enveloping the body, and you have very thin shock layer and also very thin boundary layer. So here you have very strong vortices and entropy gradients through this curved shock. And you have also high temperature flows and very strong thermochemical processes. And this shock wave is a converter of kinetic energy into internal energy. So the temperature will go up. And you will have a lot of complex thermochemical processes. Due to the fact that you have a thin shock layer, you have also an interaction between the entropy layer and the boundary layer. So this is a very complex physical configuration for the numerical methods, because at the same time you need to be accurate and you need also to be very robust to cope with the shock wave, and very accurate to discretize properly this very thin boundary layer, sorry. So the mathematical model is very well known. This is the model of the Navier-Stokes, compressible Navier-Stokes equation. In blue, you have the hyperbolic part, the non-viscous, non-heat conducting part, which is very well known under the name of Euler equation. And at the right-hand side, you have the viscous stress tensor and the heat flux here. So we use classical constitutive laws plus an equation of state, which might be a little bit complex because due to the thermochemical processes at play in such a flow, you cannot use the classical gamma gas law. Usually you have very complex model. This is why I mentioned that for real-life hypersonic flows, a larger number of equations has to be solved. Usually you have all the chemical species, but in our case, since we are interested in designing a numerical method, we will start simply with the classical Navier-Stokes equation, knowing that the extension to non-real gas effect is not a problem, okay? So, up to my knowledge, most of the existing production codes for hypersonic flows relies on finite volume discretization. This is a non-exhaustive list of very well-known simulation code. The only one is the code that has been designed by Dassault people, Michel Mallet and Frédéric Chalot. This is the ITER code, and this code is based on SUPG formulation, very original one. And it is a very nice work. So in our case, we will opt for a finite volume discretization. So finite volume discretization stems from the integral form of the conservation law over computational grids, blah, blah, blah. The cornerstone here is the interface flux approximation. In terms of the average value of the cell surrounding the targeted cell, okay? And you have two possibilities, either node-centered finite volume scheme or cell-centered finite volume scheme. Here we opt for this choice, okay? And we will use it both for hyperbolic and viscous heat conducting part. And we want also to work with unstructured grids. And we will discretize the hyperbolic part using a shock capturing approach, not a shock fitting approach. It's also a possibility. Solving hypersonic flows is still a challenging task. Okay, you have a very nice monography by Kitamura, which dates back to the 2020. In which you have a collection of different numerical methods. You have the AUSM A, B, C, D, E, F, G, etc., etc. You have almost 24 variants of the AUSM method, and all of them have troubles with some types of flows. This is the motivation for designing another variant of this method. Okay, this is not a criticism, okay, because I don't pretend to achieve the ultimate perfection, but this is this is characteristic of what we want to cope with. That is, those flows are very difficult to compute, and up to my knowledge, at that time, I estimate that we do not have the perfect scheme, okay? That's why we still work on this, because we still have to cope with the trade-off between robustness and accuracy. For sure, we need sufficient numerical dissipation to cope with the shock wave, okay, and avoid instabilities, but we don't want to degrade the boundary layer resolution, which is essential if you want to capture correctly the heat flux. And for people who are doing engineering about re-entry flows or the design of re-entry vehicles, the accuracy with which you compute the heat flux is essential. It is crucial because this will be the cornerstone to design a thermal protection system, okay? And so you really want to have this guy computed correctly. And this is very difficult to compute it, okay? Because a lot of people are showing you the pressure, okay? But the pressure is not a problem. The pressure coefficient is not a big deal. The very challenging problem is this one. And so what we observe that most of the numerical methods exhibit a very strong sensitivity to the quality of the computational grid. And we have two main classes of numerical methods here, the multi-block structured grid, and in this case you have a flow, you have a grid which is almost aligned with the flow in the boundary layer, for instance, and like this you are quite sure to have a good accuracy with classical numerical methods. But if you want to mesh a very complex geometry, this will be really painful. Okay, it can take 1 month to mesh a complex geometry. On the other side, you can deal with unstructured grid, with tetrahedral grids, for instance. So it's very easy to mesh a complex geometry, but the price to pay is that you need to work a little bit more on your numerical method. And a little bit more, it's an euphemism, okay? Because sometimes it does not work at all. So there is a lot of people now who are fighting and trying to say, now, if we use mesh adaptation, this will solve everything. I'm not completely convinced by those arguments, okay? Because I think it's not only a problem of mesh, it's above all a problem of numerical methods. We need a numerical method which is able to cope with the mesh irregularity, the mesh anisotropy, etc., etc. On our case, we have an intermediate approach in the sense that we are interested in hybrid grids. So it's not new, but hybrid grids can be a good trade-off between multi-block structured grid and fully unstructured grid. For instance, if you want to mesh this capsule, spatial capsule here, you can use an hybrid grid like this. So you have a core of tetrahedral elements, and along the surface of the ARD here, you have a layer of prism. Okay, so you start with a triangular mesh on the surface body, and then you extrude the triangular to get a prism. And then you have a match here with the tetrahedral grid, which is quite natural. But you need your numerical method to be able to cope with this type of mesh. Okay. I will finish my long introduction by saying that it is a long-term work. In fact, we have started more than 10 years ago. And the first step was done here in this PhD thesis with Rémi Abgral. It was a work devoted to the design of finite volume methods in 2D on unstructured grids for essentially the heat conduction and the viscous part of the Navier-Stokes equation. And the hyperbolic part was treated using classical row type scheme, okay? And then we had another PhD student more recently with whom we have been working on the design of a new type of finite volume scheme for the hyperbolic part. And here we are making the synthesis of all this previous work, and we are trying to improve also the previous work, going to 3D for Navier-Stokes on any type of unstructured grids, okay? And so the co-advisor is Raphaël Loubert. So our main interest here is to have a robust method. And so we want to have a positive preserving, we want to have positive preserving approximate Riemann solver for this method. And we will use what I call the multi-point flux approximation, which stems from previous work here. I don't want to go into too much detail, but why I am calling those methods multi-point flux approximation, it's in opposition to what I call two-point flux approximation. Usually, when you are solving using finite volume method multi-D problem, you have a cell, okay, like this, and then let's have a quadrangular cell. You have neighbors like this. So you have on a structured grid, you have all those neighbors. And when you compute the time evolution of the mean value in this cell, usually you are solving approximate Riemann problem on the boundary of the cell like this. And each time the flux approximation on this face depends on the two states on both sides of this face. This is what I call a two-point flux approximation, okay? And like this, you see that for a structured quadrangular grid, you have a 5-point stencil, okay? In our case, what we want to do, we want to involve also the diagonal neighbors, the other neighbors, introducing a multi-point flux approximation. This is the main idea, in fact, and I can skip all the slides after, because it's technical details. I imagine that you know the governing equation, so the multi-D Euler equation with a classical assumption on the thermodynamic closure. Eta is the specific entropy. We assume that we have a potential, a convex internal energy and a complete equation of states, assuming that the absolute temperature is positive. And so this system is hyperbolic. You have the eigenvalue here. D is the dimension of the space, and A is the isentropic sound speed. And for sure, this system is equipped with an entropy inequality in order to discriminate the physically admissible solution when you have discontinuous solution. Okay. So we are interested in designing a interface flux approximation. To construct the flux approximation, we will use the cornerstone given by the approximate Riemann solver, okay, the notion of approximate Riemann solver. So for this, we need to define the Riemann problem, and I take the tensorial flux here and I projected it along the normal direction n. Let's say that n is a normal direction to the face of the mesh, okay? And I define this 1D Riemann problem. I have also the corresponding entropy inequality, and in local notation, there is a little abuse of notation because I'm using the notation related to the normal and the tangential component related to the face. So you recognize the decomposition of the velocity. And I just want you to notice that the flux admits this decomposition between two parts, an advective part here with the normal velocity and a kind of Lagrangian part. Okay, so this natural splitting will be the cornerstone of our numerical methods design. We will reproduce this when we will build our Riemann solver. So let's go to the notion of simple approximate Riemann solver. This notion has been introduced by Gallis more than 20 years ago. We don't want to use an exact Riemann solver because it's not, practically speaking, it's not possible to use it due to the complexity and the cost of this approach. That's why we go to an approximate Riemann solver. So I recall you that this approximate Riemann solver is an approximate solution of the Riemann problem I have shown you before. This is a self-similar solution depending on these self-similar variables, and we introduce free wave speed because this is a complete Riemann solver, okay, that mimic the solution, the exact solution to the Riemann problem. And when we set this approximate Riemann solver, we introduce what we call the intermediate states, the UL star, UR star here. And what we want to compute the solution when we have two discontinuous states on both sides of an interface. And we want, from this state, we want to go to the flux, in fact. So the intermediate states are written like this. So I introduce some unknowns, rho is star, all the components of the physical variables here. And I will introduce also intermediate fluxes. And you can notice that I will use the same decomposition. I mimic the physical decomposition in between advective and Lagrangian part. I impose this decomposition to the intermediate fluxes. So it's a rather strong hypothesis. And with this hypothesis, I will be able to build my approximate Riemann solver. How do I proceed? I will simply write conservation relation across the wave. It's a kind of Rankine-Hugoniot relation because I want my solution to be conservative across each of these waves. And so I will start to write a conservation relation across the left-sided and the right-sided waves, and using this decomposition, and I assume that the wave speed are given. Okay, so I don't want to go into the detail of this, but if you make if you count the number of unknowns and the number of scalar equations, you arrive to this conclusion. So we have not enough scalar equations, so we need to make some assumption to close the system. And what we gonna do here is that we will impose the continuity of the normal velocity, which is a rather natural assumption. Here, this is the contact wave, and we want the normal velocity to be continuous through the contact, okay? But we will decide to keep a discontinuity in between the pressure, intermediate pressure. This means that we will have a discontinuity through the contact wave between the left and right-sided pressure. This is a rather strange assumption, but this will be the key to derive something different than usual, okay? Because if I assume PL star equal to PR star, then I will have an equal number of equations and unknowns, okay? And the system is closed, and we will finish with a classical Riemann solver, HLLC type, in fact, okay? It's not really a HLLC, but it's very close to HLLC if we do that. So if I maintain the number of unknowns, one more unknowns than equations, I can use one of the unknowns as a parameter. And this is precisely what I will do. I will use Vn star as a parameter, okay? And I will show you how I will use this parameter. And now, if I'm replacing the decomposition of the flux here and here inside the Rankine-Hugoniot equation, and I simply write the first component of those equations, which is related to the mass density, I end up with two mass conservation equations through the left-sided wave, the right-sided wave, like this. And since mass is conserved through those waves, I can introduce what I call mass flux parameters. It's just a change of unknowns. I will introduce the small lambda, which are the Lagrangian mass, in fact. All these manipulations amounts to come from the Eulerian world to the Lagrangian world, in some sense. I am making a kind of change of variables, in fact. And so if I introduce those small lambda L and lambda R, then I can define the wave speed, the Eulerian wave speed, in terms of the small lambda parameters. And I have the right to do that if and only if those compatibility conditions are satisfied. You can observe that this equation is exactly is equivalent to that one, and that one to that one. Okay, and that's why I have written this. And so, if I introduce this small parameter lambda L, lambda R, my conservation relations boil down to those expressions. The advective part has disappeared, and it remains only the Lagrangian part. And here you have the big U divided by rho, and that these are the Lagrangian conservative variables, in fact. Okay? And so if I develop completely the left-sided and right-sided equation, I end up with those two systems of equations for the left wave, the right wave. And these are a kind of Rankine-Hugoniot equation. But beware, be careful. This is not exactly the Rankine-Hugoniot equation due to the fact that here PL star is not the pressure given by the equation of state. It's an unknown, okay? And I can, so I have still 2D plus 5 unknowns for 2D plus 4 scalar equation, and I have my parametrization using the parameter Vn star. Now it remains to enforce positivity. That is, I want the specific volume in the intermediate state to be positive. I want the specific internal energy to be positive, and I will show you how to obtain that. I need to express the lambda zero wave speed, the contact wave speed, remember, and I need also to determine the interface flux to fit the finite volume discretization. So this is explained in this computers and fluid paper. If you tune the lambda, the small lambda, then you can find values of lambda that will ensure the positivity of epsilon s étoile and star and tau s star. Okay, and so this is the expression. This is non-linear expression because it depends also on the parameter. Okay, this simply means that if you need to have enough entropy, you simply open the fan of the solver. Okay, and once you have this, then you have the wave speeds ordering, which is very important for us. That is, you can ensure that the right wave is the right wave, the left one also, and the contact is in between, which was not obvious at all, knowing that Vn star is the parameter, okay? And for entropy stability, you have also a very strong result. It is possible to also tune the lambda parameter to ensure that you will have entropy stability through across the wave, okay? Now, how can we determine the lambda zero wave speed, so the intermediate wave speed? So we write also a balance across this wave, and we use the decomposition into advective part and Lagrangian part of the flux and the intermediate flux, and we arrive to this equation. And for sure, we want to simplify this equation as far as possible, and that's why we decide to set lambda zero equal to Vn star, the parameter. And if we do that, we do not finish with something which is equal to 0, because it remains the difference between the Lagrangian flux, LR star minus LL star, that is the difference between the pressure. Remember, I have assumed that those two pressures was not equal. So, for sure, if I assume that those two guys are equal, then I am conservative and it's finished. Okay? This is the classical way of defining the numerical methods. Now, let's play a little bit with the theoretical framework introduced by Arten, Lax and Van Leer in their very famous paper, the paper where the HLL theory has been introduced, the approximate Riemann solver theory. So you can define what I call the left-sided and the right-sided flux on both sides of the interface. Those formula, which seems to be a little bit strange, are easy to obtain. It is sufficient to go in the, you play with the XT diagram, and you integrate the XT diagram on the left side, on the right side, and then you obtain those two half flux on the left side, on the right side, okay? And so if I plug inside those formula the expression of my approximate Riemann solver, I end up with this expression of the left-sided flux and the right-sided flux, here and here. And the O minus and O plus symbol refers simply to the negative and the positive part of the wave, because you have an upwinding for sure, okay? And so once you have this, if you compute the jump between the left-sided and the right-sided flux, you end up with this formula. You simply make the difference here, and you have this guy, okay? Usually, this guy is equal to 0, because you are conservative. And this is the HLL consistency condition. If you read carefully this paper, you will see that Arten has written this condition saying, well, I want to design an approximate Riemann. I want a condition to be sure that my approximate Riemann solver will be consistent with the integral form of the conservation laws. But this is precisely this condition. So in our case, if this guy is not equal to 0, we are not in agreement with the classical theory, okay? And we will check that, because if we take all the conservation relation through the wave of the solver, we sum all these equations, we arrive with the final equation saying that the jump between the left-sided and right-sided fluxes at the interface is equal to this guy. And so conservation holds in the classical sense if and only if this guy is equal to 0, okay? So I rephrase several times, sorry. Now let's see what is the expression of this guy. We need to come back a little bit to those expressions here, and you notice that if you make the summation of this momentum, normal momentum equation here and normal momentum equation here on the right side, then you will see PL star minus PR star, okay? And you have an expression in terms of the Vn star parameter, the mass flux parameters, and that guy has this expression. That guy is nothing but the approximation of the normal component of the velocity interface using a classical Riemann solver, in fact. And so this means that you have the following alternative for the parameter Vn star. Either Vn star is equal to Vn bar, so the pressure are equal, the scheme is conservative, and you end up with a classical finite, approximate Riemann solver and finite volume scheme. Or you decide to not have this equality, and so you lose the classical framework, and you need to invent something different, okay? And so how to compute Vn star and restore the conservation property when Fn plus different from Fn minus? That is the question. So I will skip this one. Now let's go. I did not answer to the question. I will answer after introducing the discretization. It's okay? Okay. So let's go to the finite volume discretization. I will introduce something strange that I call the subface-based finite volume discretization. What is a subface? A subface, it's a partition of a face, okay? Imagine that you have general polyhedral cells. I take the example of an hexahedral cells here. So it's in 3D. I'm not very gifted for drawing a 3D picture, so be indulgent with my bad quality drawings. So if you draw the barycenter of the face, then you take the midpoint of each edge, then you can define this subface here. It is a warp surface because this is a quadrangular surface, so 4 points in space that do not define the plane. Okay, so that's why we split it inside triangular subface in order to be able to define a unit normal to the subface. So you can, in practice, you can do this decomposition with whatever polyhedral cells you have. And so the main idea here is to decide to have a subface-based finite volume discretization in the sense that the flux here is approximated on each subface. That is, instead of making a summation over all the faces of the polyhedral cells, now we are making a sum over all the nodes of the polyhedral cells, and for each node we are collecting the contribution of all the subfaces. Okay? And here, for instance, for this node, we are collecting those 3 contributions. So let's draw a picture which maybe will be a little bit clearer. If we take a look at this hexahedral cell, then we collect all the contribution, okay, looping over the nodes, okay. And for the tetrahedral cell here, it is the same, okay. Now it remains to define what is this subface flux. Okay, so the same story. We defined a Riemann problem along each subface. A Riemann problem in the direction of the normal to the subface, so the NPCF stuff. Well, P for point, C for cell, F for face. It's quite easy for French people. And I will use, to compute my flux here, I will use a parameterized Riemann solver, exactly the Riemann solver I have defined previously. And the parameter will be the Vn star velocity, okay? And here the left and the right state are UC and UD, and Xi is the classical self-similar parameter. And I will use the definition of my subface flux using the left-sided part of the numerical flux, using the Riemann problem here. That is, I am taking the contribution from the cell, okay? And this guy can be computing using the definition of the flux I have introduced previously. And a priori, the contribution from the left side and the contribution from the right side to the subcell PCF here will not be equal. And this means that we will not have a classical finite volume, a classical conservative finite volume in the classical sense. Okay, so it's a little bit perturbing the first time. So if I use an adaptation, a quite obvious notation adaptation here, I can define my flux. This is exactly the same definition than previously. So the notation are a little bit cumbersome, but this is the notation. Well, it's you have to play with local and global notation at the same time, which is not completely easy. But you have all the waves related to this interface, in fact. Okay. The left-sided, the middle, the contact wave, and the right-sided one. And you take only the negative part, okay? And this is interesting, because if you plug this inside the finite volume scheme, and you rearrange the term, you end up with this combination. And it's very interesting because you can observe that all those coefficients here are positive, and the coefficient sums to 1. And if you impose that this one will be positive, then you will end up with a convex combination. And you have an explicit inequality on the time step to ensure that. And this is a kind of CFL condition because it involves the volume of the cell, the surface of the subcell, and the negative part of the wave speed. Okay. So it's an explicit condition, and since you have the convex combination property, remember, I was able to show that tuning the mass parameter, the mass flux parameter, I can ensure the positivity of the intermediate state of the Riemann problem, okay? And then, if the time step is sufficiently small, I can ensure also a convex combination property. With this, I can demonstrate that my scheme will preserve positivity and entropy stability. Finish, okay? And this, in practice, never fail. So it's very interesting from the point of view of robustness. Now, it remains to solve a paradox and a very big question, how to ensure conservation, because we want conservation at the end of the day. So this is a quite naive approach here, simply ignoring the boundary condition. I want my finite volume scheme to be conservative. That is, I want this guy to be equal to 0 when I make the summation over all the cells. So if I replace this by the flux, I will have a summation over the cell, summation over the node of the cell and the face, the subface of each node. I can switch the summation on the node and on the cell like this. And I will simply take this part saying that this is a sufficient condition to ensure conservation. And in fact, I move from cell to point, and I'm simply saying that I will have a condition for enforcing conservation locally around each node, in fact, using the subface flux contribution. So if I work a little bit more, this is simply collecting the jump in between the flux on each subface and deciding that those jump sums to 0 around each node, okay? And so I will skip this one. I can change a little bit the notation because in 2D maybe it's easier to understand. We have a fragment grid around this node, and on each edge impinging at the node, you have two fluxes, the left-sided and the right-sided contribution. But the local conservation at the node simply state that the sum of the jump around the node multiplied by the length of the subface here is equal to 0. This is the condition, in fact. And this is the condition in the previous slide with Rémi Abgral, we have worked recently, and we have shown the link of this formulation with the residual distribution scheme, in fact. And this condition amounts to a consistency condition in the sense of the residual distribution. So it's very strong in the sense that you have an underlying Lax-Ventropf-Kind theorem, which can prove the conversion with the weak solution. So it's very, very interesting. Now, how can I finish? I will simply finish by remembering that, where it is, the jump in between the left-sided and the right-sided flux is simply expressed like this, okay? Or in terms of the Vn star and the Vn bar. So this is the end of the story here, because if I replace the expression of the jump between the flux, I will end up with this equation in Vn star, which is the parameter. This guy is known, these guys are known also. So it's a vectorial equation. I need to satisfy it on each component. And so if I project onto the component, I will end up with this equation, this equation. I have as much unknown as I have faces around the node. Okay, so rather plenty unknown. So I have not, once more, I have not enough I have not enough equation to close the system. So I will use a closure assumption, which is rather natural, saying that each Vn star parameter for each face, this is simply the projection of a nodal velocity onto the normal to the subface. Okay. And if I do that, I end up this time, so I plug Vn star Pf equal to Vpf. So in this equation, the vectorial equation, that one will be satisfied immediately, in fact. and I end up with a vectorial system in VP, which admits always a solution, provided the grid is not degenerated, that is, provided you don't have flat elements, okay? And so VP is computed solving this system. So it's very interesting because it coincides with a scheme that we have designed more than 20 years ago in the Lagrangian framework. And in the Lagrangian framework, we need to move the mesh. That's why we need a nodal velocity. In fact, this is the extension of a previous work done in the Lagrangian framework. And like this, we have the V and star parameters, and we can compute the flux, and the problem is solved. Okay. So this is a summary of the scheme, and in this framework, we will have a connection with all the neighbors around the node, in fact, due to this nodal solver. Because this nodal solver, this is a conservation around all the cells that surround the node. Okay. So at the end, we have two types of finite volume scheme. The classical one, which is phase-based, and you have a stencil, which is the built using the neighbor by the faces, and in our case, we have a stencil which is constructed using the neighbor by the nodes. Okay, so there is more multidimensionality in what we are doing. Okay, I don't pretend that I have solved a multi-D Riemann problem. So I will skip this because this is some variants of two-point finite volume scheme, because we have also, well, we don't need it. So I want to show you what is the impact of this type of approach. So for that, we are interested in solving quite annoying problem that have been listed previously a long time ago by James Quirk. A very nice paper in EGNMF, more than 30 years ago, a very long time. And this is the 3D extension of this type of test. So the test is very simple. You have a structured grid. It's a tube here, okay? And you put a perturbation on the center line. I don't know if you see it. So the idea is to move the node on the center line and to perturb a little bit it with a very small amplitude. Here for the figure, it's a very big amplitude. But in practice, we will compute the propagation of a shock wave through this perturbed grid and just see what happens. Okay, it's very interesting. So it's a Maxis right ongoing shock wave, and we observe the results after a rather long time. Normally, you should obtain a 1D solution unperturbed. So if you use what I call two-point scheme here, it's a kind of HLLC scheme or row scheme, whatever you want. If you take a scheme that preserves contact discontinuity and shear wave, it will give you this. Okay, if you put HLL, a two-wave scheme, an incomplete Riemann solver, you will stabilize this. And here, we have put an amplitude of perturbation 10 to the minus 9. Okay, so it's a very tiny one. And with our multi-point scheme, nothing happened. Okay, it's due to the fact that, in some sense, this is my interpretation. We have here a numerical dissipation which is really multi-D, in fact. Whereas here, it is not the case. Here, this is classical Riemann solver with 3 waves, and the numerical dissipation is oriented along the normal direction. Okay, you have nothing in the tangential direction. Whereas, for us, here, we have both. Okay. Another interesting feature is this is the set-off problem. It's completely different. It's not hypersonic. It's hypersonic flows, but it's well, there is an analogy. This is a point blast problem. Okay, at time t equals 0, you have a cold medium, and you put a Dirac of energy at the center, and you will see the emergence of a self-similar solution, a shock wave, a radial shock wave. And so if you use a correct setup, you will have a radius of shock at time 1 equal to 1, and you will have, with the gamma equal to 7/5, you will have a peak of density at 6, okay? Gamma plus 1 divided by gamma minus 1, the classical asymptotic. So it's just interesting to observe the solution at time t equal 1 for the classical two-point scheme and for the multi-point scheme. You see, normally you should have the spherical solution, okay? But we compute it on the Cartesian grid, and so the classical finite volume scheme gives you this, okay? Which is rather ugly. You can improve it if you go to second order, if you refine. But what is satisfying is that with this multi-point scheme, from the very beginning, you have something satisfied, even with a crude grid. And moreover, here, I don't know if you noticed, but you have also the beginning of instability here, like carbuncle ugly stuff, okay? So just to see what it does on real test case, so this is the ARD test case. You have, in this paper, you have a lot of interesting test case. So atmospheric re-entry demonstrator. This is a demonstrator built by ESA, and it has I don't remember when, but I think that there is a flight test regarding this. Okay, so you see that you have Mach 24, you have a very big angle of attack, and it's very painful, particularly in the rarefaction wave here, because you have density close to 0. So if your scheme is not able to withstand this, it crashes. And so I will just show you qualitatively what happens with the two-point scheme, like HLLC or Rho scheme. So you have a very big protuberance here, which is symptomatic from the carbuncle instability, okay? In our case, so this is a mesh made of tetrahedra, if I well remember. In our case here, the solution is clean, okay? So another more complex test case, the pre-X, so this is the EXV vehicle, also from ESA. It was a pre-demonstrator. So it is a little bit more complex because you have a flap here. And when you want to mesh this guy using a multi-block structure grids, you will spend quite a long of time to mesh this part, believe me. So it's Mach 25, and it's also quite challenging. So this is a tetrahedral mesh here also. This is Eulerian computation up to second order, and it does not crash at all. And just to assess the accuracy, we have plotted the pressure coefficients for different gradient computation for the second order, compared with the Navier-Stokes code. And so we plot the pressure coefficient along two planes. There is one plane here along the mid-axis, and another plane along the mid-plane along a flap, okay? And that's why you have difference here and here, in fact. And so you have discrepancy with the Navier-Stokes solution due to the fact that on the flap you have recirculation that we cannot capture using the Euler computation. But we were quite satisfied to obtain this. Because we have a quite good agreement everywhere. So let's move now to Navier-Stokes equation. So we start with a supersonic flow over a flat plate. Just want to show you the sensitivity of the results with respect to what we do for the hyperbolic part, in fact. Because people think that, well, what is important is the heat conducting and viscous part. I don't think so. Because, well, you need to pay attention to heat conduction and viscous part, particularly when you play with cell-centered finite volume scheme, because it's not easy on unstructured grid. I don't have enough time to detail what we have done here. But what is very important is to see that depending on what you do for the hyperbolic part, you will have a great impact on the heat flux and on the field in the boundary layer, in fact. So this is the rather classical test case. This is an adiabatic flat plate. at Mach 1.7, so not very classical mesh. We mesh the boundary layer for sure. So the velocity field, the temperature field, and what is interesting to observe, the profile of velocity with respect to the normal coordinate, in fact. And so at first order, for the hyperbolic part, you observe that the free wave scheme, like an HLLC or rho scheme, is quite accurate, okay? If we use a two-wave scheme like HLL, you have only two waves, a left-sided, right-sided, and you have a mix in between. You don't capture the contact, neither the shear wave, okay? And so you have a lot of dissipation of the boundary layer that produce this, okay? And forget the modified free wave, okay? And the multi-point scheme is here, okay? So not far from the free wave scheme, okay? Because the multi-point scheme is able to preserve the contact discontinuity, okay? But it does not preserve the shear wave. But it has a good behavior on the shear wave independently of that fact. And so when we go to second order, everybody converge to the reference solution, but you see the effect simply on having a more accurate solution in the boundary layer, okay? So, a more classical test case, this is a cylinder flare configuration. It is an ONERA very interesting paper, and the configuration has been set up at that time to have a 2D axisymmetric solution to validate code. In our case, we are in 3D, so we need to mesh the 3D geometry, so it's a rather costly test case. And this is a Mach 9.9 configuration. And so at first order for the hyperbolic part, for the pressure coefficient, well, not very good. For the flux, not good at all. And you see the huge discrepancy between the different variants of numerical method. So you really see, the Stanton number is the normalized heat flux. You really see the sensitivity to the numerical method. When we will go to second order, we will have a more converged solution. So for the pressure coefficient, all the schemes give you almost the same result, okay? For the Stanton, it's another story because we have discrepancy. And for instance, the HLL-like scheme will be above, okay? And the multi-point is quite close. The multi-point is here, is quite close to the experimental results. So we are quite satisfied. And so let's progress toward more demanding test case. So this one is a very hard one. It's almost Mach 20. It's taken from a very nice website from NASA, NASA Langlais. And so they proposed a set of benchmark for hypersonic. I will stop here. And so we will use a classical hexahedral mesh. And so if we take a look at the pressure coefficient, it's okay. Nothing to say. And we have a reference which is the LoRa legacy code from NASA Langlais. Okay. And if we take a look at the Stanton number, so at first order, it's a huge mess. In fact, you have LoRa here. So the multi-point is not far from LoRa, but it's not, we use the same mesh than LoRa, in fact. And the other one are completely, when you go to second order, it's a little bit better, but it depends on what you are doing. With second order, we are playing with we know-like combination of gradients, in fact. That's why you have linear combination and non-linear combination. And you see really, even at second order, the influence of the way you are doing the second order will change the results for the Stanton number, so for the heat flux. We still are happy because the multi-point flux is still behaving quite reasonably. And now, maybe the most challenging, you decide to play with an hybrid grid with prism, okay, near in the boundary layer and tetrahedra elsewhere. And so even for the pressure coefficient, it's not obvious, but the multi-point is coping with this quite reasonably. Okay. The other one experience troubles. And if we go to the heat flux, it's a nightmare. Okay. At first order, the multi-point is the behavior of the multi-point is rather good. At second order, when you have a linear combination of the gradient, it's it's erratic. And for a non-linear combination, it's a little bit better. In fact, what we observe is that if you have perturbation inside the shock wave, this will propagate till the boundary layer, in fact, and this will put the mesh inside the boundary layer. So you really need to pay attention to the way the shock wave is resolved. And unfortunately, with triangular tetrahedral cells, they are not aligned with the shock, and this creates noise that propagates through the flow after that. Okay. So I don't know anybody obtaining good results on such configuration, because people who are playing with the mesh adaptation, they are cheating a little bit, because usually they put very tiny cell at the boundary, and when you ask them to show you a zoom on the solution, you have oscillation on the heat flux, in fact, and they explain to you that they need to put some smoothing. Or here we do not do any smoothing. This is the net results from the numerical method, and it's only finite volume. Okay. So my conclusion is that hypersonic heat flux computation is still a challenging task. Okay. If I have a word to say, the multi-point scheme brings something new and something quite interesting with respect to robustness. We are working on many directions. We have done an interesting work regarding the Lomac extension with my former postdoc Alessia Del Grosso. We are also working a lot on the time implicit discretization, because the results I have shown you are also obtained using a time marching algorithm. Okay. We are working on the Haley formulation, because this nodal velocity, which is used to compute the flux, is very interesting also to move the mesh, if we want to move the mesh and have something intermediate between Lagrangian and Eulerian configuration. And we are continuing to fight with the Navier-Stokes computation, and I hope that in few weeks we will have more interesting results. And this is the main objective of Vincent Delmas, and the PhD defense will take place next spring, so we are approaching the end. And this is some, okay, thank you for your attention.
Microphone to ask a question.
Thank you very much. Really nice and very original scheme. Of course, I have plenty of questions, but maybe I have a question of something you haven't talked about in the presentation, which is the second order extension of your scheme, because you didn't give any detail about how you are doing that and how you capture shocks in that case. So maybe you can comment. And it's a bit related to what you were saying for maybe also the mesh adaptation scheme, because what happens is that when your grids become very anisotropic, if you use least mean squares to compute the gradients, the least mean squares are ill-posed, and so you have to go to weighted least mean square or something special to handle that is conditioning, I guess. Yeah.
I fully agree. Thank you for the interesting question. In fact, for the second order extension, we have done a muscle Hancock type extension, that is because we want to save time. Okay, because when we are in 3D, everything is very, very expensive. And so first we decide to have a one-step second order extension. That is, we compute space and time extrapolation of the solution within each cell to feed the Riemann solver with the extrapolated values at the nodes and not at the phase center as it is done usually. This is the first point. To compute this space and time extrapolation, we need to compute time gradients and space gradients. So for the time gradients, we use a Lax-Wendroff-like elimination, which is rather easy to implement. And for the space gradient, we use an evaluation of the space gradient using a discrete operator. We are able to define discrete gradient and discrete divergence operator using the subface decomposition, in fact. And it's a kind of green gauss approach for approaching the gradient, okay? Because because when we start with least squares, we were facing what you said. It was a nightmare, and moreover, since here we have neighboring by the nodes, you can imagine that for tetrahedral cells, you have a huge amount of neighbors by the nodes, and for when you use least square approach, it's almost impossible, in fact. This is the only way we have found to obtain something satisfactory. Okay, but we have spent quite a long time to find it. And for the stabilization, we use a kind of nonlinear weighting because this is a combination, a nonlinear combination of gradients.
Take the gradients which compute the smoothness cost.
Exactly. But it's written in the paper, in the GCP paper.
You. So thank you. Really fascinating seminar. I wanted to go back to page 38. And so here, I don't understand really the meaning of the figure on the right. You seem to say that it shows that the multi-point scheme is much better, but there are still oscillations. So I'm not sure I understood what you want to say here.
We plot the density isosurface in 3D. This simply means that because you have a shock wave which is propagating. No, it's not an oscillation. Yeah, exactly.
Okay, so this is really good.
Yeah.
And if you go to page 40, I have a really stupid question.
No problem. But I just want to emphasize here that for me, this is very mysterious test case. Those test cases has been introduced by Quirk in 2D because Quirk was playing with AMR at that time and he was facing very strong difficulties with AMR grids due to round-off machine error, in fact, but instability were propagating. And so this is only conjecture because this test case is very often related to the carbuncle instability. Because when you are prone to develop this type of instability, normally your scheme will develop also carbuncle instability. But on the way around, we don't have any results. Okay. So sorry.
LANL.
Los Alamos National Laboratory.
So it's a report from LA.
Yeah, exactly. No, I know. Once I've been assaulted, also attacked, yeah, very violently by a Russian guy in a conference, because he said to me, well, the Sedov problem has been solved by Sedov and not by this stupid cam from yes. It was very funny. I was surprised. After that, we discussed a little bit, but I said, well, for sure, this is the Sedov problem. But Cam has done a very nice work in the sense that he has proposed a kind of normalized setup to obtain very easily the solution. Okay.
So this is probably not the same cam that I know. I know Roger cam from
No,
MIT.
Jim cam.
Team cam.
Yeah, thank you very much. It was very nice and clear for a complex topic. So
Thank you.
thank you. I have a very naive question: is that all these schemes, they in a way try to regularize the shock. So they introduce, subgrid scale dissipation or mechanism to regularize. How do we know it? There aren't physical mechanisms which are not taken into account, or which you could add, which would give you a physical regularization. Of course, yeah, there is some physics because, for example, the entropy condition is physical, right? But if I imagine that in this very high, Mach number, then you would have, ionization, all sorts of mechanisms which can regularize the shock. So would it be interesting to look at these mechanisms to add them to numerical schemes, maybe?
I think you can do a lot of things. You have, for instance, people have derived, it dates back to Deshpande, if I remember well, kinetic scheme for hyperbolic, and the idea was, you take the Boltzmann equation, you project onto Maxwellian, and then you get, and it's easy to take into account advection in the phase space than the, and so this is, and now you have, I don't remember his name, Professor Xu from Hong Kong. He's very prolific, plenty of paper, but what he call UGKS scheme. It's a quite interesting approach also to obtain the scheme for the Euler equation. Here we are facing always the same stuff. It's very interesting from an historical perspective. For me, it dates back to Los Alamos once more, where von Neumann and Richtmeier decided to solve compressible gas dynamics written in Lagrangian representation, and they decide to adopt a rather physical point of view, and they need to stabilize the shock because otherwise they were solving the entropy equation. That is, the entropy was conserved along the trajectory of the fluid particles, and they observed that they were facing instability. So they decided to put a physical mechanism. They called it an artificial viscosity. And they decided to localize it also using a sensor related to the divergence of the velocity. But it's ugly in some sense, but when you want to go to 2D, how to deal with the shock in 2D, how to tune the coefficient in front of the artificial viscosity. And that's why Godunov's approach is also interesting because it's the opposite. Saying, well, I want to deal with something which is conservative. I solve the detailed solution at the interface, that is the breaking of the initial discontinuity. I solve the Riemann problem. I compute the flux from this. But when I'm doing that, I do not take a look at the dissipation mechanisms, because the dissipation mechanisms are embedded inside the Riemann problem solution. And at the end of the day, I am solving a total energy equation, and I have dissipation, but I don't control this dissipation. When you use a Godunov type scheme, for instance, if you want to compute a rarefaction wave, the result is ugly. We have test case, a rarefaction wave in the vacuum, for instance. You will see an increase of temperature at the interface with the vacuum, which is completely unphysical. And so I don't know what is the good approach. Maybe in between, because nowadays a lot more and more people are using scheme based on artificial viscosity. People playing with Galerkin discontinuous method, for instance. They put the people at you remember Jaime Perrer and the team at MIT. The team at MIT, they are playing with artificial viscosity. But, it's very tricky. If you want to do that, you need to tune the artificial viscosity in order to obtain good solution. Otherwise, I don't know any universal numerical method that answer properly to this problem. Because we need dissipation, that we need entropy. But we don't have an equation on entropy. This is the problem. We have an entropy inequality. So how much entropy shall we need to stabilize properly a shock and not to degrade the solution of a rarefaction wave? This is a very interesting question, indeed.
What about dispersion? Does dispersion matter? I mean, is it a mechanism which, because it is a mechanism which also regularizes the shock, right?
I'm not a specialist, so I don't have any idea about that, but it's also probably a path to investigate, for sure. So there is still work to do, n'est-ce pas? Yes.
Schemes, because you can bound those situations. So it's a very old theory by talk.
Yeah. I remember also. But
I have a very naive question. I've seen that in the applied math community, the HLLC scheme is very, very frequently used. But there are many other, I suppose, schemes, ENO, Quick, Super B, TVD, etc. So why is LLC so popular?
It's popular. If we make the history, I like history. It's very interesting. And so at the beginning of the 80s or at the end of the 70s, people were fighting to obtain easier numerical methods to cope with this problem. And so first you have rho. So the paper of Rowe, it's 81, but if you take a look at the technical report from the Royal Aeronautic Establishment, at the beginning, when it's very interesting to read the historical paper by Rowe also, when he told the story about the discovery of the scheme. And HLL theory, it's 81 and 83. There are two papers about that. And so the Rowe scheme is a little bit difficult in the sense that you need the eigenstructure of your hyperbolic problem. If you think about MHD, it's a real nightmare. Because you have 7 or 8 waves, and the structure, the Rowe solver for the MHD, it has been solved partially by Braillot and Vu with gamma equal 2, and Gallis did the job maybe 10 years later at the beginning of the 20s. And if you go to more complex system like elasticity, for instance, it's the HLL theory by Arten, Lax, and Van Leer is easier in the sense that they propose a framework, a general framework, saying, well, we don't need the fine structure of the Riemann problem. We just need something in average, okay? Because when you compute the flux, you will average over the cell the fine structure, the fine wave structure. And so they set up a condition to have consistency. This is what I call the HLL consistency. And they propose also a numerical method named HLL with only 2 waves, the 2 extremal waves. But at the end, when you do that, you have a kind of averaging, okay? But it's very robust. You can show a lot of results on it. You need to determine an accurate approximation of the wave. And the main drawback of HLL is that you don't preserve the contact wave, okay? And people were fighting to obtain something more accurate during the 80s. And with a lot of different investigation. And at the end of the day, that was a Toro with Spears in 1994 or 2, I don't remember. They have this idea to introduce the supplementary waves. And in the HLLC approach, you have to approximate the wave speed. And the writing of the numerical methods is rather easy. And you can handle whatever physics you want, and that's why I think it is so popular. But you need to play with the approximation of the wave speed, which is not completely obvious, okay? In our case, we have a formalism even for the what I call the free wave scheme, in which the wave speed are determined in a systematic manner from the Lagrangian to Eulerian transformation. We don't need to build approximation of the wave speed. They are part of the solution itself, okay? And that's why this is also an improvement of the HLLC stuff.
You had other questions.
Actually, follow-up of this, because one of the inconveniences of the Riemann solvers is that if you move to more complex hyperbolic systems, in general, you have to reinvent your Riemann solver, and sometimes for the approximate raw Riemann solver, for instance, you have no unique definition of the raw average for complexity. So maybe you can comment about possible extension, for instance, to complex chemistry, because we are doing hypersonics. So at some point, I guess that you want to add the transport equation for chemistry and so on. And then I maybe another more philosophical.
Okay, no, but I have the micro also. Yeah. Yeah, for sure. If we want to enrich the physical model, for sure, we need for hypersonic to add a lot of advection, diffusion, reaction equations to take into account the chemical disequilibrium, eventually also the thermodynamic disequilibrium if we have several temperatures, electronic temperature, vibration, rotation, etc., etc. So we have more complex mathematical structure, and the way we have constructed the Riemann solver is easy to extend, in the sense that we only need to have a structure in which you have a decomposition of the flux into an advective part plus a Lagrangian part. And it seems that most of the continuum mechanics models are like that. Okay, we just need that to construct the Riemann solver, and I don't need any assumption. I don't use the gamma gas law in my Riemann solver. The only things I need to know is the isentropic sound speed. And normally, if I have a good hyperbolic structure, I have real wave speed. Otherwise, we don't play with. It's not hyperbolic, and I don't want to know about it. Okay.
The last question is about the fight between smart low-order schemes and high-order schemes, because what you show is that many of the defects you can see in the first-order schemes tend to be, let's say, reduced when you move to higher order. And actually, if you go to higher and higher and higher order, even conservativity becomes less critical, because you have a conservation error, but it becomes the order of approximation of your numerical scheme. That's why, for instance, some people use, I won't say non-conservative schemes, but for instance, they can use chimera grids. In that case, you have conservation error, which come from interpolations on chimera grids. So, yeah, I'm on the very high order side of the force, but of course, I'm not trying to do industrial hypersonic flow configurations. So
it depends on the point of view, for sure. I completely agree with you. If you want to take a look at very fine physics, for instance, like laminar to turbulent transition using LES, DNS, for sure, there is no way you can't do that using this type of framework. Okay, for us, one of the main problem is related to robustness, because we don't compute one configuration. Usually, we compute a full trajectory. And a full trajectory, it's several hundred calculations, okay? And it's not only one trajectory, it's 10,000 trajectory, because we investigate what we call a flight, the flight envelope. And so when you want to compute like that, if the code crashes every trajectory, every computation, it's a nightmare. And moreover, we put more physics on it, because usually we do multi-physics computation when we couple the flows with the aerothermal response of the TPS. Okay, and that's why there is a crucial need for robustness. And with this type of shock wave also, I think that it's very difficult to go to very high order because you need to withstand the shock. By the way, we have an ANR project that starts next year. About the name of the project is hypersonics, and the idea is to investigate the benefit, the eventual benefit from very high order to the computation of such flows. So I will give you the answer in 3 years.
Thank you very much.
Very much in favor of a wide discussion, and so but it's quite late. So unless someone has a very, very short question, I will thank you again.
Thank you very much for your attention.
Pierre-Henri, we will be here this afternoon, so if you want to meet with him, please come to see us. Sorry.